Today's topic frames ecological landscape planning through the lens of climate adaptation and urban flood risk. The central argument of this presentation is that resilient urban form cannot be achieved through isolated technical fixes alone. It requires a systems perspective that connects ecological structure, planning policy, digital analysis, and multifunctional blue-green infrastructure. In this lecture, flood modeling is used as a particularly useful entry point because it makes invisible spatial processes visible, where runoff accumulates, where exposure intensifies, and where planning intervention can most effectively reduce risk. As we move through the presentation, keep in mind that ecological planning is not only about adding green elements to the city. It is about reorganizing relationships among land, water, vegetation, infrastructure, and vulnerability so that the city can adapt more safely and more intelligently under changing climate conditions. The session follows a clear progression from concepts to applied evidence. We begin by asking why ecological planning matters now, especially under intensifying climate pressures and urban exposure. We then move into frameworks and planning logic, showing how policy agendas, urban ecology, and resilience thinking guide spatial decision-making. The next section focuses on tools, particularly GIS, BIM-style coordination, and parametric scenario testing, because these help planners diagnose risk and compare alternatives. From there, the lecture turns to intervention logic through nature-based solutions, multifunctional green infrastructure models, and sustainable water management. The final section addresses implementation, governance, and best-case evidence, especially recent studies on flood risk modeling in urban basins. This sequence is important because it mirrors how ecological planning works in practice. First define the problem, then interpret the system, then test options, and finally translate evidence into design and planning action. By the end of this topic, students should be able to explain the basic concepts of ecological approaches in landscape planning and understand why these approaches are increasingly necessary in climate adaptation. A second objective is to interpret planning frameworks and policy directions, including the European Green Deal, urban ecology principles, and nature-based solutions as an applied implementation framework. Third, students should be able to analyze ecological risks using GIS, BIM-style coordination logic, and parametric design workflows. Fourth, they should be able to translate that analysis into nature-based and multifunctional green infrastructure proposals. Finally, the topic also aims to build a professional attitude. Ecological planning requires interdisciplinary collaboration and inclusive practice. For that reason, technical knowledge alone is not enough. Students must also learn to think across scales, sectors, and stakeholder groups when proposing resilient landscape planning strategies. Ecological planning has become urgent because climate extremes are intensifying at the same time that urbanization is concentrating exposure in vulnerable areas. Flood, heat, drought, and ecosystem stress increasingly overlap rather than appearing as isolated hazards. In many cities, sealed surfaces, fragmented green space, low-lying development patterns, and overloaded drainage systems amplify the impacts of extreme rainfall and heat. Conventional gray-only infrastructure often responds to one problem at a time and may even transfer risk elsewhere instead of reducing it systemically. Ecological planning offers a different logic. It links space, water, vegetation, and social vulnerability within one planning framework. This means that planners do not simply ask how to drain water faster, but how to reduce runoff generation, restore ecological function, and prioritize intervention where both hazard and vulnerability are greatest. In this sense, ecological planning is not optional enhancement, it is a core adaptation strategy for contemporary cities. At the heart of ecological landscape planning is the idea that landscape should be read as a connected socio-ecological system rather than as a collection of separate land parcels. One key concept is patch corridor matrix logic, which helps planners understand ecological connectivity and identify where blue-green networks are continuous, fragmented, or missing. A second concept is ecosystem services, which make the benefits of landscape visible across sectors by showing how ecological systems support cooling, runoff regulation, habitat, and public well-being. A third concept is multifunctionality. Instead of allocating land to a single purpose, ecological planning prefers interventions that perform several roles at once. Adaptive capacity is also central. The system must be able to absorb disturbance, reorganize, and continue functioning. These concepts matter because they shift planning away from static land use assignment and toward dynamic relationships among ecological structure, risk reduction, and long-term urban resilience. Ecological planning is guided not only by design ideas but also by policy and planning frameworks that help translate broad goals into operational decisions. At the European scale, the European Green Deal promotes climate neutrality, circularity, and ecosystem restoration, creating a strategic context for adaptation-oriented planning. Urban ecology contributes another layer by reframing the city as part of ecological processes rather than separate from them. The nature-based solutions framework is especially important because it offers a shared language for designing, delivering, and evaluating ecological interventions. However, these broad frameworks only become meaningful when they are translated into local plans, adaptation strategies, regulations, budgets, and site-scale design briefs. Municipal plans are therefore the bridge between policy vision and physical implementation. They determine where risk is prioritized, how investments are phased, and how blue-green infrastructure becomes part of real planning and maintenance systems rather than remaining a conceptual aspiration. This slide introduces ecological risk framing as a way of broadening conventional risk assessment. In standard terms, risk is often understood through hazard, exposure, and vulnerability. Here, adaptive capacity is added explicitly, because the ability of a place to respond and recover is also part of ecological resilience. In landscape planning, this means we must map people, assets, ecosystems, and lifelines together rather than separately. Priority areas are typically those that are dense, low-lying, highly sealed, and socio-economically vulnerable. A flood map on its own is therefore not enough. We need to understand where runoff overlaps with weak ecological structure, where vulnerable populations are concentrated, and where there is an opportunity to improve adaptive capacity through planning action. Risk maps should not be treated as final outputs. Their real value lies in guiding design decisions, investment sequencing, and the selection of spatial interventions that reduce both immediate hazard and long-term fragility. GIS is one of the most important tools for ecological planning because it allows planners to combine multiple forms of evidence in one spatial decision environment. Typical layers include topography, hydrology, land cover, imperviousness, soils, drainage, demographics, and the location of critical assets. When these are overlaid, planners can identify hotspots where runoff risk, heat exposure, ecological fragmentation, and social vulnerability converge. This type of analysis supports hotspot mapping and suitability mapping, which are especially useful for prioritizing intervention zones. The value of GIS is not simply visualization. Its real strength lies in making complex interactions legible and comparable. When combined with multi-criteria analysis, it can help rank areas for zoning change, phasing, and investment. For ecological planning, GIS therefore becomes the analytical base from which landscape structure, risk reduction, and social priorities can be interpreted together and translated into defensible planning choices. After priority areas are identified at district or city scale, analytical mapping must be connected to project implementation. This is where GIS to BIM style workflows become useful. GIS is strongest for spatial diagnosis across wider territories, while BIM style coordination becomes valuable at project scale where detailed relationships among topography, utilities, buildings, drainage paths, and planting systems must be resolved. The key contribution of this workflow is coordination. It helps design teams reduce clashes, clarify phasing, and connect strategic planning decisions to buildable detail. In ecological planning, this matters because adaptation success depends not only on good analysis but also on whether interventions can actually be constructed, maintained, and updated. The broader lesson is that digital tools should not be treated as isolated platforms. They work best as a chain in which large-scale diagnosis, site-specific coordination, and long-term operation and maintenance are linked within a coherent planning and design process. Parametric design introduces a more exploratory and adaptive way of testing planning and design alternatives. Rather than locking into one preferred solution too early, planners can generate and compare multiple scenarios by varying storage volume, section geometry, slope, planting mix, permeability, or other performance-related inputs. This is valuable because ecological planning always involves trade-offs. A design that improves runoff control may influence access, cost, habitat quality, or thermal comfort in different ways. Scenario testing helps make these trade-offs explicit. It also supports safe-to-fail thinking by allowing teams to explore options before implementation and compare how different solutions perform under uncertain futures. In practice, this makes decision-making more transparent and more robust. It encourages iteration rather than premature certainty, and helps planners identify alternatives that align ecological, social, and technical performance more effectively across a range of possible conditions. This slide turns from analytical logic to intervention logic. Nature-based solutions treat vegetation, soils, and water processes as infrastructure rather than as decorative add-ons. In urban contexts, the toolbox includes green roofs, rain gardens, bioswales, urban wetlands, permeable paving, and floodable parks. The key message is that these elements should not be selected as isolated fashionable devices. Their appropriateness depends on site conditions, catchment function, maintenance capacity, and the wider blue-green network in which they are embedded. A rain garden, for example, performs differently depending on slope, inflow patterns, soil conditions, and downstream connections. Network effects therefore matter more than isolated devices. Ecological planning uses this toolbox strategically, selecting and arranging interventions so that ecological processes do work within the city. The planning value of nature-based solutions lies in their ability to combine adaptation, ecological restoration, and public space improvement through integrated rather than single-purpose design. Ecological planning gains strength when green infrastructure is designed as a connected and multifunctional system. This means one intervention can buffer floods, cool public space, improve habitat, and enhance urban amenity at the same time. A floodable park, for instance, can operate as temporary storage during heavy rainfall while also supporting shade, biodiversity, recreation, and everyday public use. The same principle applies at district scale, where connected corridors and linked storage systems usually perform better than one-off projects. Multifunctionality is important not only ecologically but also economically because it can increase resilience and long-term value for money. Instead of investing separately in drainage, cooling, habitat, and public space enhancement, planners can design systems that deliver several of these outcomes simultaneously. In that sense, multifunctional green infrastructure is not simply a greener version of conventional planning. It is a more integrated model of urban performance, where ecological and social benefits reinforce one another. Water management is central to ecological climate adaptation, and this slide introduces a circular logic for thinking about urban water. Instead of treating rainfall as waste to be evacuated as quickly as possible, ecological planning aims to capture water near source, slow conveyance, store it temporarily, infiltrate or reuse it where feasible, and monitor system performance over time. This approach supports flood reduction, soil moisture, vegetation health, and resource efficiency simultaneously. Circularity matters because stormwater can become a resource within urban metabolism rather than just an emergency burden. At design level, this may involve detention areas, infiltration zones, reuse systems, or visible blue-green corridors that hold and redistribute water more safely. However, long-term performance depends on maintenance, monitoring, and attention to local hydraulic conditions. In ecological planning, sustainable water management is therefore not just a technical drainage issue. It is an organizing principle that links resilience, ecology, and circular resource thinking. This slide emphasizes the distinction between fail-safe and safe-to-fail planning. Traditional fail-safe approaches often rely on rigid barriers and single design thresholds, which can produce severe consequences when exceedance occurs. Ecological resilience instead prefers distributed, redundant, and modular systems that can contain damage and recover more safely when limits are exceeded. In practice, this means designing public space to flood safely rather than attempting to eliminate all water everywhere, creating overflow routes, sacrificial areas, recovery plans, and redundant storage. The broader planning lesson is that uncertainty must be accepted rather than denied. Climate extremes cannot always be predicted precisely, so resilient systems should be able to absorb shock without catastrophic breakdown. Safe-to-fail thinking therefore complements ecological planning because it encourages flexibility, recoverability, and controlled disruption. It shifts design attention from absolute protection toward damage limitation, adaptive performance, and post-event recovery capacity. Ecological planning is inherently interdisciplinary because no single profession can fully address the interactions among hydrology, ecology, engineering, governance, and public health. Landscape planners must therefore work with ecologists, engineers, utility managers, emergency managers, and communities. This slide also emphasizes inclusion. Community knowledge can improve diagnosis because residents often know where water accumulates, where heat is most severe, and which places feel unsafe or neglected. Inclusion also matters for legitimacy and equity. The same intervention can benefit one group while burdening another if priorities are not openly negotiated. For example, adaptation investments can trigger unequal amenity gains or place maintenance burdens on already underserved communities. Ecological planning therefore requires participatory thinking throughout diagnosis, design, implementation, and monitoring. In this sense, resilience is not only technical. It is also social and political, shaped by whose knowledge counts, whose risks are prioritized, and how benefits are distributed across the city. Many ecological plans are persuasive at the conceptual level but fail during implementation. This roadmap shows how that gap can be reduced. The first step is diagnosis. Establish baseline conditions across risk, ecology, public space, and infrastructure. The second is to set measurable targets before choosing interventions so that design decisions respond to explicit outcomes rather than vague aspirations. The third step is piloting, because small but strategic projects can create quick wins, test performance, and build institutional confidence. The fourth is scaling through regulation, capital programs, maintenance routines, and monitoring systems. Finally, monitoring closes the loop by showing what should be adjusted, expanded, or redesigned. This sequence is important because ecological planning is not a one-time design act. It is an iterative governance process. Successful implementation depends not only on good projects, but also on institutional learning, budget alignment, maintenance logic, and performance evidence. Metrics are essential because ecological planning must demonstrate performance rather than rely on good intentions alone. The slide organizes metrics into several groups. Hydrological measures include peak flow, inundation depth, duration, and storage performance. Ecological measures include canopy cover, habitat connectivity, vegetation and soil health, and biodiversity proxies. Climate-related performance can be tracked through shade, surface temperature, and cooling contribution. Social and delivery dimensions include access, equity, safety, cost, and maintainability. What matters here is not just measuring one category well, but linking hydrology, ecology, climate, and social outcomes within the same evaluation logic. A design that reduces runoff but produces inaccessible or poorly maintained space is not a strong ecological planning outcome. These metrics therefore help planners assess trade-offs, compare alternatives, and monitor whether implemented schemes continue to perform over time under real and changing conditions. The Shanghai case demonstrates how planning policy itself can function as a flood risk intervention. In this study, future land use simulation using FLUs is combined with LIS flood FP hydrodynamic modeling to compare business as usual, growth as planned, and eco-constraint scenarios under RCP 2.6 and RCP 8.5 climate pathways. The significance of this case lies in the fact that flood exposure is not treated as a fixed background condition. Instead, the study shows how different development trajectories produce different risk outcomes by altering where urban expansion occurs and how much land becomes exposed to inundation. The eco-constraint scenario reduces future exposure by shaping growth more carefully. The planning takeaway is powerful. Land use regulation is not separate from adaptation, but part of adaptation. Ecological planning therefore begins before site design, at the scale of spatial policy, protected areas, expansion control, and the strategic structuring of future urban form. This comparative slide brings together multiple case studies to show how digital evidence can support resilient planning decisions in different ways. In Algiers, ArcGIS and Urban are used to model drainage network performance and identify upgrade priorities. In Jinan, GTAHP critic weighting combined with GIS supports defensible flood risk zoning by aligning modeled zones with historical flood-prone points. In Zhengzhou, 1D, 2D InfoWorks ICM simulation is linked to a hazard vulnerability method that reveals higher risk in low-lying, dense river edge areas. In Baoji and Linyi, two-dimensional modeling is validated through official reports and social media incident data, showing that predicted flood depths correspond closely with observed events. Together, these studies show that resilient ecological planning is strongest when it is backed by explicit modeling, transparent weighting, and multi-source validation. The design lesson is clear. Planning decisions become more credible when digital tools are used not only to predict, but also to verify and prioritize. To conclude, ecological landscape planning treats the city as a connected socio-ecological system in which policy frameworks, spatial diagnosis, digital modeling, and design action must work together. Nature-based solutions are most effective when they are networked, multifunctional, and maintainable. Circular water logic, safe-to-fail thinking, and inclusive planning all strengthen resilience because they address not only hazard reduction, but also long-term ecological and social performance. The case studies reinforce that point by showing how evidence from modeling, weighting, scenario comparison, and validation can guide better spatial decisions. The overall message of the lecture is therefore twofold. First, ecological planning is a way of thinking about urban systems relationally. Second, it is a way of organizing evidence so that climate adaptation becomes actionable at multiple scales, from spatial policy to site-specific intervention and long-term governance.